Let's consider the orbitals now. Let's look at our s, our p, our d, and our f orbitals. So remember, our s orbitals, they're just going to be a nice sphere. P, we get that dumbbell. D, we get the four-leaf clover, or that dumbbell with the donut. And F, they're complex. I'm not even going to try to draw an F orbital. All right, so let's get into it. Let's take a look at our s orbitals. And actually, this is kind of our s orbitals, remember, they only have one spatial orientation. And so when I have plural on here, the s orbitals are like the 1s, the 2s, the 3s. Okay, we're only going to get one orbital per subshell. All right, so our s orbitals, these are spherical in shape. They only have that one spatial orientation. We can only get an m sub l equals 0 because for our s orbital, our l equals 0. So the only m sub l we can get is also 0. So when I look at, my 1s, l equals 0, m sub l also equals 0. Okay, now here's the thing about our orbitals. They contain nodes. So when we look at this, remember, we are not orbiting the nucleus. Our electrons are bouncing around. And so what we can do is we can get these probability density maps that give us the probability of finding an electron in the atom. And so our nodes are where the probability of finding an electron goes to 0. Because remember, we get wave-like behavior of our electrons. And because of that, we can get destructive interference. We can get places where the waves cancel each other out. And in those places, we're not going to have any chance of finding an electron. Okay? And so here we've got this probability density map. So if I'm looking at a 1s orbital, okay, my n equals 1, my l equals 0, and my m sub l equals 0. And so I have this probability density map. So you can see on the left side there, I've got all these dots. And the closer together the dots are, the more clustered they are, the more likely we are to find an electron at that position. All right. And so the further we get away from the nucleus, you notice the probability of finding an electron drops down. And then we can get this shaded in circle there, which is showing 90% probability of finding an electron in those spaces. All right, and so we can get this 1s radial distribution function. And so that maximum there, that's the maximum distance from the nucleus that we are likely to find an electron. And we have a maximum probability there, all right? So this 52.9 picometers in this 1s orbital for this particular atom that we have solved the Schrodinger equation for, we have the maximum probability of finding an electron at that 52.9 picometers. So what this means is max okay? So that's what that means. All right, now when we think about the nodes, okay? So I have a string there so you can see as it goes. And so here, there would be a node. There would be a node. Those are places where it cancels out and the probability of finding an electron drops to 0. So if you notice on my cutaways here for this 2s and this 3s situation, that we get a probability that equals 0 at the nodes. Now, if you notice for my 3s, all right, so this is this one right here. Okay. If you notice the probability, function there, what's interesting is, all right, the greatest thing is under here, okay? That corresponds to our n equals 3, because it's further away from the nucleus. But I don't have a 0 probability here or here. One of the things that we're going to explore, not in this particular chapter, but later on in the course, is we're going to explore this idea that because the electrons bounce around all the time, even though we have an electron that normally lives, for better terminology, in the 3s orbital, it bounces around, and so sometimes it will actually slip into the 2s or the 1s, and it will penetrate deeper into the atom than its normal spot. It doesn't spend a whole lot of time there. You know, the probability of it being, closer to the nucleus is much lower than its normal, home in the 3s orbital, but that doesn't mean it's 0. Same thing over here. We've got the greatest area under the curve there, under that 2s distance, but there is a little area under the curve there at the 1s distance. All right? So we can look at further cutaways, and again, you can see where, we've got these radial probability distributions of finding electrons, and then we've got those spots where it drops to 0, where we get that destructive interference. If the cutaways are hard to look at, here's the exact same thing, but looking like, a flat pancake. All right, so that's with our s orbitals. Okay, now let's move on to the p orbitals. Now, this is a little more straightforward because with our p, remember, we have an L equals 1, so we can get an M sub L of -1, 0, or +1. And so within the p subshell, there are 3 orbitals. Okay? All right, and so they're dumbbell shaped. We have those 3 different spatial orientations, and so we have 1 nodal plane. So for our p orbitals, our L is equal to 1, which is why we can get the M sub L of -1, 0, and +1. All right, so, for example, if we have our 2p, okay, here we have an N that would equal 2, and L that equals 1, and then when we look at our M sub L, we do the -1, the 0, and the +1 across like that. And so because we have 3 M sub L values, we have 3 orbitals in the p subshell corresponding to 3 different spatial orientations. And so you can see here the px, the py, the pz, and then them overlapping. We have 1 nodal plane that exists between the dumbbells. So in that in-between zone, we would have a probability of finding an electron of 0. But in the lobe of the dumbbell, that's where we have the probability that we would find an electron. Okay. And so here you see the density mapping, where the more dense the little tiny red dots are, the more likely we are to find an electron. Okay, all right, d orbitals. Okay, so within d subshell, we have 5 orbitals. All right. And this comes from the fact that a d orbital has an L value of 2. So I have 5 possible M sub L values because I have -2, -1, 0, +1, +2. I get 2 nodal planes here because we've got our 4-leaf clovers in 4 different spatial orientations. Then we have that weird dumbbell with a donut. Okay. So let's say I have a 3D. So if I'm in 3D, my N would equals 3. If I'm D, my L equals 2. And then when I look at my M sub L, we would go -2, -1, 0, +1, +2. Okay? All right, and so here you can see the 2 nodal planes that exist to separate the 4 lobes of the 4-leaf clover from each other. And so within the nodal plane, the probability of finding an electron would be 0. And then within the lobes, that's where we would have the probability of finding an electron. Okay, if I take all 5 of those d orbitals and I superimpose them on each other, now we get an even crazier picture, but it starts to look a little bit more spherical, right? Okay, and then we get to our f orbitals. And so within the f subshell, we have 7 orbitals. Because now within our f subshell, our L value is going to be 3. And so our m sub L, -3, -2, -1, 0, +1, +2, +3. Okay. The f orbitals are crazy. There's 7 different spatial orientations. They're super complex. There's 8 lobes all over the place. We get these 3 nodal planes. And again, in the nodal plane, that's where we have a probability of finding electron goes to 0. And so let's say we have the first time F shows up is in energy level 4. So let's consider a 4f orbital set here. Our n would equal 4. Our L would equal 3. So f orbitals L equals 3. I forgot to put that up there. And then m sub L, again, we would just go down the line, -3, -2, -1, 0, +1, +2, +3. Okay? And so we get all those crazy shapes. Like I said, I'm not even going to try to draw an f orbital. My drawing skills are tested by d orbitals well enough, but these are what the f orbitals look like. They are pretty crazy. And then when I superimpose everything, that's when we get that picture that we are used to seeing of a spherical shape for our atoms. Okay? So this is how our quantum numbers are corresponding to our different orbitals.